and thank you for giving me the opportunity to show some of our results in this conference. Today I'll talk about strong coupling in organic semiconductor slab microcavities. Before I, sorry, why is it moving? Sorry. So before I go into the results, I want to discuss a bit about the motivation of our work. And very recently, a new field, an emerging field called Polaritonic chemistry is getting a lot of attention. And this is a crossroad, let's say, of quantum electrodynamics and chemistry, where it has been shown that when you strongly couple to various vibronic modes, you can change the energy, the chemical landscape, and you can change the rate at which molecules undergo different chemical reactions. And here I put some examples from recent papers, actually from Everson's group, who is really active in this direction. And as you can see, for example, you can strongly couple to the OH stretch of water, and you can retard the enzymatic activity of the enzyme pepsin, or you can have vibronic strong coupling of the reactant in the solvent and accelerate the solvolysis of a molecule, or even go a step forward and have some sort of selectivity by changing the size at which you strongly couple, and then you can retard or accelerate a particular reaction. So in general, these kind of experiments have been done in a microfluidic-based microcavities, this is the existing microcavity configuration. It become kind of a default now. This is taken from one of the Everson's paper, actually. And as you can see, there's a microfluidic cell where you can deposit two mirrors either side of the cell, gold mirrors, and then you can put a silica spacer layer, and there's the inlet and outlet where you can circulate the solutions that you contain the species that you want to strongly couple to. So it seems that this is a delicate microcavity structure, and particularly you don't have easy physical access to the strongly coupled molecular species. And having a so interesting field where you can alter chemical reaction rates, and you can actually it can actually attract attention for applications, for example, in synthetic chemistry. And therefore, maybe we're wondering if there is a simpler geometry where we can use to perform Polaritonic chemistry, and also maybe an open resonator where you can have physical access to a strongly coupled species. Therefore, we try to design a new structure to accommodate this, and this is a new structure, a dielectric slab microcavity, where it's actually a silica slab which is deposited on top of niobium oxide, and then on top we can deposit our organic materials, and therefore the refractive index contrast between the interfaces of organic air and silica and niobium oxide allow for photons to be confined inside the slab, and therefore we create a cavity structure where we have a confined optical field. So we have simulated our structure using a transfer matrix model, and as you can see, the different layers are defined by their refractive index with these black lines, and also by the shaded areas. And as you can see, this structure consists of 200 nanometer niobium oxide, 2.3 micro of silicon dioxide, and an organic layer on top of 250 nanometers, containing for this particular simulation an inner layer. And as you can see, the field is confined inside these layers here. And here at the organic area, you can see that we have an electric field amplitude that is high, and as I will show later, is high enough to allow for strong coupling to be observed. And before I show any results on strong coupling, we have measured the reflectivity of just the two dielectrics, the bilayer of the dielectric, so therefore without any organic layer on top, so niobium and silicon oxide on top. And as you can see, this angular reflectivity that we can measure from these structures. It has a Q factor that is around 33 as we calculate from our simulations and experimental data, and we can find different order modes that are in the vicinity of the wavelengths that we would like to work. Again, this is without any surface organic layer. And now what happens if we introduce an organic top layer? And for this, we have used a J-aggregated cyanide dye dispersed in a gelatin matrix. J-aggregates are really good materials for strong coupling because they have very high oscillator strength and narrow absorption light widths. And so we create this gelatin aggregate blend in solution, and then we can spin coat this a film on top of our structures. And we have done so, and we spin coated a 250 nanometer layer on top of this structure. And as you can see, we observe different modes that show the characteristic anti-crossing around the energy of the excidons at angles where the photon and exciton become degenerate. And we have extracted a bi-splitting energy of around 72 MeV for this splitting, and using a condition for strong coupling given by an old paper from Savona, we showed that actually our structures meet the condition for strong coupling. So we indeed operate within the strong coupling regime. So we so far showed strong coupling, but we want to think a step forward and say, why not try to do some chemistry on these states while are on the surface of this slab. So we have switched to a new molecule, a porphyrin molecule, mesotetraphenyl porphyrin, MTPP, which was dispersed in a polymer, polystyrene. So we have selected this molecule because, again, it's a good molecule for strong coupling. In fact, the first demonstration of strong coupling, I think, was shown by using a porphyrin molecule. And for another reason, because porphyrins are used in sensors, and they have some sensor activity. So this molecule has a solid band, which we name S1, around a 421 nanometer. This is the absorption peak. But when exposed into HCl, hydrochloric acid, we can protonate the porphyrin ring, and then we shift the absorption peak at around 447 nanometer, which we name S2. This process it's reversible. So when we expose the molecule to ammonia, we can deprotonate the molecule, and we can recover the original unprotonated molecular species with the absorption at 421. So we have taken this solution blend, and we spin coated control film. And as you can see here, with the control film, we have measured the absorption of this film. And when unexposed, we show the S1 peak at around 421 nanometer. But when we take the control film and put it in a chamber for various times, and the chamber includes either hydrochloric acid or ammonia, we show that after 5 seconds, hydrochloric acid vapors, we see that a second peak emerges corresponding to the S2 solid band. And here we have a coexistence of the two molecular states. And as we expose it further, we see that the S1 is suppressed and the S2 becomes more intense. And as I said earlier, this effect is reversible. So if we take the same film, put it back in ammonia vapors, we see that we can reverse the process. We can protonate the molecule, and we get back the S1 peak, which starts to reemerge. And after a long time, we see that we have almost recovered the original spectrum of porphyrin. So now we think we decided to put this film instead of a control free, create a film on top of our slab microcavities, and we have coded our structure that I showed previous with these molecules, and we have measured the reflectivity of the structure at various times after exposure. And as you can see, for the unexposed molecule, we observe, as expected, strong coupling around the S1 mode, which is around 421 nanometer. And as we expose the molecule for 5 seconds to hydrochloric acid vapors, we see that we get a three-way hybridization where we observe strong coupling around both S1 and S2, and we see this the emergence of these middle branches, which suggests the coexistence of the two states, S1 and S2. And as we expose further, we see that we suppress splitting around this energy, and we get splitting around the energy of S2 solid band. And again, this process is reversible. So exposing to ammonia, the same structure, we go back to the three-way hybridization where we have the middle branches with the two and different species on the surface of our slab microcavity. And then after a long time exposing to ammonia, we go back to the original strong coupling to the S1 mode. So actually we have shown that we can do some sort of chemistry on top of our structures, and we probe this protonation process with time, and we try to see plot the interaction energy of the two states with time, exposure time. And as you can see, before we expose the cavity into any gas, we get splitting of the S1, and we get around 85 MeV interaction energy, with S2 being absent. While after few tens of seconds, we see that we cross over from weak to strong coupling regime defined by these two regions, and vice versa for the S1 from strong to weak coupling regime. So we can actually have some sort of sensor activity, and we can have a measure of molecular state concentration by using strong coupling. And as one will wonder, that many of experiments I show in my first slide were done, and maybe when molecules are immersed in a solvent or in the liquid environment. We have tried to examine whether our structure are compatible in an aquatic environment. So we took our structure and immersed it in a vessel full of DI water and tried again to measure strong coupling in this kind of structure. And as you can see, we observe a splitting around the energy of the exit on S1, which is measured to be around 145 MeV, and again it satisfies the condition for strong coupling. And so our structure work within in a liquid environment as well, and can operate in the strong coupling regime. So now the question is, can really this structure be used to modify reaction rates in our microcavity geometry? So all the studies so far were done with vibrational strong coupling, and therefore, although we haven't done yet experiment with vibrational strong coupling, we have simulated by changing our structure and making a structure which is infrared compatible, and therefore we have to change the different layers and use layers that are using infrared spectroscopy. So we have using selenite, calcium fluoride, and PMMA, and we wanted to strongly couple the infrared mode to the double carbon-oxygen bond of PMMA at around 5.7 microns. And indeed, again, our structures, as you see from the plot here, the 2D plot in the transfer matrix simulation, also the couple oscillator in white, we get values that satisfy the condition for strong coupling. And therefore, our structures are indeed compatible with IR spectroscopy and vibrational strong coupling. So to conclude, we have shown that we fabricated a new microcavity structure based on a dielectric slab. We show strong coupling of molecules that are on the surface of the slab, and therefore the molecules are open to the environment. And we have performed simple chemistry on the molecules that are under the strong coupling regime. And we show that our structures work in both gaseous and aquatic environments. And simulations show that we can shift by selecting the right materials and thicknesses to accommodate vibrational strong coupling in these structures. And therefore, we believe that these structures are compatible with a range of chemical reactions and potentially can be used as a platform to facilitate Polaritonic chemistry. So with this, I want to thank my collaborators in Sheffield, especially David Lindsay, for all the contribution to this work, and also thank you all for your attention.
Thank you very much. This paper is open for questions. I don't see. Okay, maybe I have one. Do you seek a sensor that would use the surface bound molecules, or do you seek photochemistry taking place at the surface with your system?
So what I have shown so far and what we have done so far, I don't think that at the moment strong coupling, if I understand the question correctly, strong coupling, I don't think strong coupling affects the rate at which any of these changes in the molecule happen. But we believe that by selecting the right molecules, for example, going to the vibrational strong coupling regime, maybe we could probe these reactions and see the reaction rates and show that they change when you strongly couple to different vibrational modes.
Okay, thank you. Any other question? No. Okay, thank you very much, and we will switch to the next